I am Marco Zecchini, and I'm a PhD student at Sapienza. And today we're going to have a class on, it's like an hands-on class, so we're gonna work with the code and see how to set up a project using pyTEAL and develop a smart contract, interacting with them on Algorand. And the thing is that, so this is the primary object, primary goal of our class today. So going through the whole pipeline of developing a smart contract application on Algorand. And but we are going to do that like with the spirit of seeing how to optimize existing solutions of adding new functionalities to those applications that we are going to see. Indeed, at first we are going to see how to set up our development environment, and we're going to see some tools to connect to the network, to set up the environment and so on. Then we're going to go through we're going to see how to develop a first smart contract account application and how to interact with it. And then we're going to see two examples, one improving the other, essentially, of the auction of an auction, okay? And I think like that Andrea already told you a bit of it. And essentially, this is to connect with what I was saying before with the idea of improving the first auction that we're going to see. It's very easy. It's simply store it's only the highest bid in the second auction that we're going to see. We are going to see how to make it more complex in order to have a sealed auction, and so we're having a more complex application. Finally, as we were discussing before, we are going to see how to also work a bit with Beaker. And yeah, so this is like the overview of our class today. So we are going to start with the setup of our environment. And to do that, we at first we need to connect to the network, okay? And we have two options to do that. Like Algorand offers us. Sorry, offers us two options to do that. And one is connecting using an external service, which is called Purestake. And where essentially this Purestake offers us a way to a set of full nodes to which we can connect to, and then it's very easy to connect to the network in this way. We simply have to create our account, sign in, and then connecting to the network using our API key. And here there are several examples on the way to do that, and it's very easy. And so this is like one way of interacting with the network, and it's you don't need to set up anything, essentially. We don't need to run any node and nothing. And the other way to do that is using the sandbox, which is a tool provided by Algorand, which essentially is a set of Docker images that we can use to connect to, and in order to create our private network or a node of the mainnet, testnet, betanet, or the things that we want. And this is the option that we are going to use today. So the way to use the sandbox is very easy. We just need to clone this repo. Okay. First, I forgot to ask you, in order maybe to be more also to make some comparison. I don't know how many of you knows like or has some experiences with Ethereum development. smart contract development in order to also make comparisons. And let me see if I can, is there a way to look at the participants? Like raise your hands if you.
I think they should be able to raise their hands.
Yeah,
or they
I'm
can
seeing
use
that
the Q&A.
there are 5 out of 32 hands raised. Okay, I expect more. Okay, so maybe sometimes I would give some, make some comparisons to the Ethereum world essentially. So okay, let's go back to our example and to our stuff. So as I was saying, we need to install the sandbox. The sandbox is very easy to install. We simply have to clone this repo. We need to have as a prerequisite installed Docker Compose and Docker, of course, in our computer, because, like as I told you, these are Docker images. So I have already copied my sandbox in my terminal. Maybe I can increase the size of. Okay. And so you just need to clone the sandbox. Of course, in my case, it doesn't work, but once we have the sandbox and we are in it, we have to launch the sandbox. It's very easy. So launching a node of a network is very easy. And we just need to type this command and specify actually the type of network we want to connect to. And there are several networks that the sandbox allows us to build. There is all those with the suffix of net, so testnet, betanet, and mainnet. Actually, maybe we can look at the Docker Compose file. We should have it specified some. Maybe it's other. Okay, it's yeah, as you see, config devnet, mainnet, nightly, release source, testnet. These are all the network that we can build essentially, and those ones ending with net are those ones which are public essentially. So the betnet, devnet, and testnet. That devnet, it's the betanet also known. No, okay, there are 2 of them. And we can also create our own private network, and essentially we need to use this other configuration: config beta, config dev, release, which is the last stable version. Dev is I guess it's the one related to the devnet. In beta is the one corresponding to the betanet. Okay. So in our case, we now, as I was saying before, setting up a sandbox is very easy. In our case, we are going to use the dev network. Would you like to restart? Yeah, why not? It takes a bit to start. More than expected. Okay, maybe let's try with release because it was already up, so it doesn't have to download any image. Permission denied. Okay. Sometimes you have to use sudo, otherwise sometimes it doesn't work. So it takes some time to run, but it eventually should work. But in the meantime, I suggest you to follow my steps. So like cloning the sandbox and running the sandbox as I'm doing. And so if in this case, if there are some problems related if there are some problems with the setup or something, we can see it together. Yeah, of course. No, sorry, I answered. I don't know how to use Q&A. I'll use the chat. I will publish the repo on the chat. So here it's not going. So maybe if it doesn't work, we should switch to Purestake. I didn't expect that, but. However, in the meantime, we can set up our local environment. Okay, so we will make it work and see if it works. In the meantime, we need to create a virtual environment. Okay, so we create a tutorial. A tutorial directory, okay. And we need to follow these steps here. Okay, we need to install virtualenv if we don't have it, and then create a virtual environment. Then activate the virtual environment. And then we need to install for our tutorial, essentially these two libraries, which are, one is the pyTEAL library, and the other one is the Python SDK for Algorand. Okay, so we need to install them. Let's see how it's going here. That, okay. Okay, maybe there is those sandboxes. I can turn it down. No. Okay, no problem. We switch to, we're gonna use, I wanted to use a private network, but apparently it's more difficult to do. We're gonna use the testnet, okay? So, and therefore we are going to use the Purestake. I don't know why it's taking so much, maybe because of, I'm also on Zoom and my computer cannot handle it. Okay, so as I was saying before, you need to create an account here on Purestake, and to connect to the Algorand daemon of these of the Purestake nodes, we have to follow this step essentially. We should also start a project in your preferred IDE. In my case, I'm using IntelliJ, but apparently okay. Now you have to use either, you can choose to use either sandbox or Purestake. And in my case, I was trying to run sandbox, but apparently, since maybe I'm sharing my screen and my screen, maybe I'm connected to Zoom, my computer that cannot handle it, and so it takes a lot to run the sandbox. So I'm connecting to Purestake, but you can choose whether to use the sandbox or Purestake. I mean, these are like two opportunities to connect, to create or connect to an Algorand network, okay? And so, come on. My computer is rebelling, okay. It's taking ages to run at AJ as well. Good. Okay, so okay. Okay. So we can create a new. I will open my the project that I have created, okay, in this window. And okay, now we need to connect to Purestake because we don't have the chance to connect to our sandbox now. So to do that, we are going to create a Python file, which we call like first, okay? And we need this snippet of code to connect to Purestake. Okay, and okay, I need to specify the SDK to IntelliJ. In my case is this. No, this is my interpreter. Okay. So he should now recognize that I have Argo SDK installed. I want to connect to the testnet. It's perfect. And I don't need to connect to the Purestake. I should need the Algo token, so you can ignore that actually. You only need to type here, to paste here your XAPI key, which in my case was this thing here. And you copy and paste it here. Okay, and it should work without any problem. Yeah. And it seems that it is connected, nothing happened, so everything's good. And so we need to create an account on Algorand. The way to do that, it's very easy. You can follow this tutorial. And we can, okay, from this link, we arrive to this page, and we have, we can go to create an account on Algorand within this page, and copy and paste it and create our actually let me just do that. Algorand keeper. So essentially what we do here is the following. We use this generate account function that gives us back the private key of our account and the public address, okay? And we print them out through these functions, okay? And in order to see them. But essentially what we are gonna need and use in the future are not these two, but what is usually used to recreate your account locally is this mnemonic passphrase, okay, which is this set of words, and that we need to copy and to recreate our account in everywhere we want, okay, and recompute our private key on everywhere, okay. So this is the address of our account, okay. We don't have. We can maybe try to go on Algo Explorer testnet. You should be able to see that this account has no balance. It hasn't done anything in the story of the blockchain. So the thing that we have to do now is, in order to use it, actually, is to provide him some funds, okay? And to do that, we should have some FASO testnet on Algorand, which is called Algorand dispenser, okay? We have to solve this captcha and provide to our account some token. So if we go here back, we see that we have received 10 algos, okay? Like also in Ethereum, we do the same things, that it's so something super common usually for start working with accounts on every testnet around. I don't know if there are questions. Sorry, I was a bit confusing at the beginning because I expected to use my sandbox, and so I was but I hope that you followed all my steps. Essentially, to resume again, we have connected to Purestake instead of sandbox. We did it live, and to do that, we just connect to this dashboard, and we use one of these. In Python, one of these snippets, which is provided by them, to create transactions, to connect to the network. And we have connected to the testnet, okay? And then we have generated our keeper, okay? And we have found our key with this tool, which is called the dispenser. The testnet dispenser. Maybe I can give you the link here. Chat that you can use. Okay. Essentially, on the sandbox, we would have done the same, but locally. So we will have some. We would have some account that owns all the tokens and could issue them to everybody. Okay. So it seems no questions so far. Okay, so now we can go further. We can start working with smart contracts, okay, and see how to create a very first example of a smart contract. And on Algorand. We're going through this tutorial. Essentially, we're going to recall these steps of some step of this tutorial available on Algorand. So I'm trying to giving you always all the materials on the Algorand documentation in order for you to go through by yourself. Essentially, I recall that every smart contract in Algorand is composed by two programs: the approval programs and the implicit program. The approval programs essentially handles all the main operations of our smart contract. And so from the creation to the deletion, it's possible to delete smart contracts on Algorand, while on Ethereum it's not possible to do that. We can update the smart contract on Algorand, which natively is not possible to do that on Ethereum. And all these, and how to handle the update, the delete, the opt-in of an account to a smart contract is handled by this approval program, but I guess you already know that due to the previous classes that you have attended. And then there is this other Purestake program, which essentially is invoked, as far as I remember, when you you want to, as I said, it suggests clear the state. So you are deleting the contract and you want to complete to manage all the final operations to clear the state of the smart contract. Okay. So we are not actually going to work in this way. Okay, having two different functions handling the two programs, because it's a bit more complicated and it's a bit like starting being a bit maybe outdated. We are going to use another tool, which is called Router, okay? And for creating and handling all our applications. And in this way, we are also, it's very easy to create an ABI, which is an ABI file, which is a file that it's something that allows developers of off-chain to invoke properly the functions of every smart contract with the proper type and of each parameters, and also the returning parameters and so on. But we are going to see that more into the detail in a while. So for now, what we have to do is creating a new file, okay, which we will call first contract. Okay, and we need to connect properly. So we need to copy this. These are these things that we have already created on the other file. Okay. So in order to connect to Algorand, okay, and then also we need a variable for our mnemonic, okay, because we want to retrieve the account that actually we fill with Algos tokens, okay, and we're going to save it as a global variable. And now what we want to do is starting creating our router, okay. The router belongs to the class, belongs to the pyTEAL module. So now we should be able to see it. And the router essentially takes as input two parameters. The name of the smart contract, we'll call it counter smart contract, counter contract. And then we need to define something called the bear codes. Okay, the bear codes essentially are a set of codes which do not take as input any parameter essentially, but in this way it's very maybe you can say in this other way. As I was saying before, there are several types of transactions that can be made to a smart contract, and there are the delete application transactions. These are actually all application transactions, but we can specify on the completion of this transaction what operations should be done. And So we have delete application, update application, clear state transactions, opt-in transactions, and close-out transactions, and so on. And essentially, in this method here, we can define for each, within this variable action, we can define for each incomplete action, okay, which is the operation that we want to do, okay? So at creation, okay, so only at creation of our smart contract, we want to do the operation that we will define in this variable here, okay? Which is a sequence, okay? When you want to do a set of operations one after the other, you use these, so a sequence of commands in the smart contract. You need to use always this command here, okay, which is sequence, both in Beaker than in pyTEAL. So it's something that works for both the framework essentially. And we want to now this first smart contract is a counter, okay? So we want to have two functions that increase and decrease the value of a global variable, okay? I hope you remind that in the Algorand Smart Contract there are two types of variables: local variables and global variables. Global variables are like the variables belonging to the state of the smart contract, while local variables are the one belonging to the state of an account within a smart contract, okay? And so we will define our variable in this way, and we need to use help global put as a comment, and for calling it again like easier in the status of a smart contract, we store the state variables as pairs of key and value, okay? So we store here, we create a variable counter key, which is essentially the key of our state variable, okay, which is of type bytes. We call it count, okay? So we set global put the counter key, so the variable count to 0, okay? So at creation of our smart contract, the creation generates incomplete this no op function, okay? We will invoke this handle that essentially saves in the state of the smart contract this state variable with identified with this key, and it initializes to 0, okay? And then the other operation that we're going to do is to approve the transaction, okay? So there are two things that I want to say here. First, I recall you that in a smart contract, the primitive type in Algorand Smart Contract, the primitive type of a variable can be either an unsigned int 64 or an array of an array of bytes, okay? And these are the two primitives formed, and then can be combined to create more advanced variables, essentially. And after that, I want to remind you that each transaction in the smart contract needs to be approved or rejected by at the end of the execution of an operation of an invocation of the smart contract. So every time you need to specify if you work in this way, like we're going to see later that you don't actually always have to do that, because there are some abstractions that the router allows us to do. But essentially, if you simply create your function, your handler in this way, you always have to specify the approve, okay? Okay, now we have one vehicle actions when we initialize the smart contract, but let's suppose that now we want to do something when we update our smart contract, okay? And in this case, we specify that we will always reject update, okay? In this case, also is in the case of the deletion. And we will ignore something that happens on the closeout. So when someone, when one accounts can opt in and opt out from the smart contract, essentially. Opting in means that you want to create some local variables, some local state variables within your account, essentially, and in this case, you ignore it, okay? And we will do that the same for all the other cases. We won't do anything after these operations are done, okay? We will simply ignore them, okay? So these are our vocal applications. Okay, yeah, maybe we can also go through the documentation to be more clear. Someone asked me if I can go again through the vocal applications. And there should be something here, I guess. Yeah. It should be okay. Otherwise, purpose. Okay, however, let's see if here there is something that I can use. Okay, as it suggests here, the documentation, essentially the Berkel actions, okay, are those operations that operations that are Berkel. It means Berkel means that when you do this kind of operation, you don't need to pass any arguments to the function which we are invoking, okay? And we can create one Berkel action, okay, for every case of the incomplete action, okay? So we will have okay, I don't know if you remember, but I tried to call that before for you. But when you create and you do an application transactions, each application transactions, on the completion of it, the smart contracts on the completion of this transaction works like so. If this transaction essentially is consistent with the previous state of the smart contract, if this transaction is valid, on the completion of this validation, the smart contract will execute its logic and validate the logic and validate the transaction again, and furtherly, essentially, not again. And we can specify which kind of action we want to do, okay? And there are these 6 types of actions that we want to do after an application transactions. An application transaction is invoked, okay? And what we did here in the Berkel actions method, we specified one operation for each of these incomplete action, okay? And And in the first one, we only at creation. So we execute the process contract and set the contract parameters. So I finish and then I answer also you. And here we execute this sequence of operations. We essentially initialize the variables, and then for all the other operations we perform. Here we ignore. We didn't do anything. In this case, we reject the operation. Okay. Okay, I first ask A, Berkholz create only deploys the contract and set the constructor parameters similar to the Ethereum constructor parameters. So yeah, somehow in this case they create only is the constructor of our smart contract. So, but we don't pass. It's like a constructor without any input parameters, okay? So it's like having a constructor that does not receive anything and in input, it only sets up and initializes the variable, okay? However, we will see later how to create a constructor without a Berkholz, because it won't be a Berkholz. Berkholz means that this transaction is not receiving any input parameter. Okay, it's simply a Berkholz. Okay, and the router lets us handle these operations in a very light way. Okay, it took some time also for me to understand this concept. So I see that there is some. So the meaning of Berkholz application, of Berkholz actions. So I can understand that there are some issues. I finished with Akshay and Akshay, sorry, maybe I pronounced it wrongly. No, here essentially the approve is that we have a sequence of operation, okay, that we specified with this command, okay? Like every time you want to execute a sequence of operations, you have to say to create a use this keyword here, this function here, and after that create a set like a list of operations that should be done. So in this constructor, let's say we did 2 operations, and the first one is initializing the variable and then approving the transactions. Like the logic of our smart contract essentially approves the transaction, saying that this is a valid transaction, can be added to the ledger. Okay. So in this case, we have to specify, like every time a transaction is approved or rejected, in this case, we are going to approve it. Okay. And we need to specify that. We are going to see later that using another method, we can also not specify that, okay? But it's not possible to do that with Berkholz, actually, that method, okay? So if I understood correctly, each of those actions are executed after the deployment, and each of these actions makes some checks on the contract. Yeah, as I was saying, like this is the constructor, okay? And after that, we can execute all these operations in the Berkholz, okay? And yeah, essentially what a smart contract does is always to modify the state of the ledger, okay? But according to a certain logic. So before modifying the state of the ledger, we are going to do some checks usually, yeah. And in this case, we don't do any checks because we are just deploying the smart contract, so we don't need to do any check, okay? Ah, sorry, I thought that everybody can see it. Okay, apparently I didn't notice that not everybody can see that the Q&A. Maybe why don't you type this on the chat that everybody can see it?
Wait, they do not have the chat, but I can enable the Q&A for everyone.
Okay, because like I thought that everybody could see it, and so I was directly answering to the Q&A, which are
It
open
is
there.
not the default. Perhaps
Okay,
now
sorry.
they can see your questions.
I don't know. Can you see also the past history of the Q&A? Okay. Okay. Sorry. So I didn't know that. Okay. I'm receiving a lot of no. I got it. Essentially, one. Please, guys, stop sending no. And essentially, they made me questions about what are the parameters of the bear calls. If this create only is essentially the constructor of our smart contract, and why there is the approve here, and that's all. Okay, mainly. So now you will see that I keep open the Q&A session, so you will see all the questions of our students, like all of the other students, like I'm doing. So you will always be updated with the questions. Okay, so let's move on a bit, and now we need to define. These are bear calls, okay, but are not actually the methods like common methods of that you can also have in Solidity. You know, think about Solidity. In Solidity, you have that a smart contract has defined within itself many functions, okay, and you can invoke the functions, sending the transactions with the specific call data that actually invokes that function. Okay, we have to do the same here in Algorand. Before the router, we did it. You always have to do that, like passing like as transaction arguments the name of the transaction we want to invoke. Now with the router, is much more easy to create a transaction. We simply create a transaction like in Python, and above it we put a decorator router method. Okay, and router should be the name of the variable that the router object has been assigned to, and method, like we can even specify something within the parentheses, and we will see it later how to do that and what we can do with that. But with this decorator, we are creating method of our smart contract, okay? And it's very easy to do. Now we want to do a function which increments a counter, our counter, okay? And to increment our global variable, we need one temporary variable to do that, okay? In which we will copy the value of our global variable, and we will update it, and then we will increment it, and then we will save it again, store it again in the global state of the smart contract. Okay. So to do that, we use like some scratch variables called, which are essentially local variables, and we need to specify for each scratch variables the type of these variables. I remind you that there are two types: unsigned int and bytes. Okay. And then we need to return a sequence of operation, okay, which would be, of course, the increment of our count. Okay, so at first we can verify that the transactions are not grouped. Essentially, this means that we are sending only one transactions, okay, packed, because in Algorand it's possible to create a group of transactions which are called atomic transactions, atomic transfers, with either are committed all together or not. In this case, we want only one transaction to be sent to our smart contract, and we want to update the value of our local variables, essentially, like function variable, I don't know, and that we will retrieve from the global variable in the state of the smart contract, and then we will save again this variable, okay, in the state of the smart contract. This time, loading the value of the scratch count. Because every time you need to load to access the value within the scratch space, and increment it by 1. Okay. Note that since now we are using this decorator here, we don't have to specify that we approve the functions, because by default it is done by this decorator. Okay. Now we have, since it's a counter increase and decrease, we want to decrease. So we want to create a function that decreases the value. Okay. And it's very similar to the one before. Something that maybe we can add is the following, is that if the scratch count load value is greater than int 0, then okay, then we will decrease our value. Otherwise, we will ignore it, because since these are unsigned int, we cannot go under 0. Okay. Other questions? Okay, no. So essentially, this is the code of our smart contract. Okay, and IntelliJ is not giving me any error, so I assume that everything's fine. Okay, so now we can define a function that we will call main that interact with our smart contract. Okay, and within these functions we can put our client. Okay. We can retrieve the private key of our account, okay, in order to sign transactions. And for doing that, we need to do a set of operations. Maybe we can create a util file, because this can be useful for you in the future also. And within this util file, we will create one, generate private key from mnemonic. Which we will pass. Okay, we need account mnemonic. Okay, for now, anything else? And we are going to retrieve the private key from the mnemonic. I remind you that the mnemonic is this string here, in this way, mnemonic, which we import from Algo SDK to private key, and we pass Okay, let me pass it back. Because he doesn't see it, because we're going to have a set of functions that we can put in our util file and then invoke anytime we want. Okay. Okay, now we have retrieved our private key, and okay, so now what we have to do is when we deploy a smart contract on Algorand, we always have to specify how many local variables, unsigned int local variables, bytes local variables, unsigned int global variables, and bytes global variable are used by the smart contract. Okay. Essentially, the approach that that Algorand use compared to Ethereum is that in order to save maybe to be more fast in computing its operations, you always have to provide all the information to Algorand to validate the state, while Ethereum does it by itself. Like at validation time, each node like increased it performs all the operations. We will see it later. Afterwards, we will work with NFTs and with the smart contracts, and so we will see to the smart contract. We will tell to the smart contract with the NFT that we are using is this one specifically. While in Ethereum, I think it's a bit different, the approach. However, we have to define the number of global int. It's 1. So we are saying that in this way that we want to only use one global variable, okay, and which is an integer. Then we don't need to use anything else. And then what we have to do is using global schema, okay, creating a global schema that we need to use created from Algo SDK in future. To which we pass the amount of local integer and no, sorry, this is a global, so it will be global int and global byte, local schema transaction, local int global. No, local bytes. Okay, so every time you have to deploy a smart contract, you have to specify how many variables you're using and different types and in terms of space and primitive. Okay. Okay, now we can compile our smart contract, and to do that, we will use this function from our router. Okay. That's what I was saying. It makes us very easy to create a smart contract. And we need to specify only the version of the Algorand virtual machine that we want to use. In this case, we use the 6th one, even though I think that there is a 7th one. But the thing is that you can use the version that you want, like the compiler in Ethereum. And it returns 3 variables: the clear program, the approval program, and the ABI. Okay, we'll see maybe now how the ABI is made, okay? And usually when you compile your program, what you do is save it in a TEAL file, okay? Oh, what's going on here? We will call counter approval as f write approval program open. Clear. Sorry, I forgot here the extension. These are TEAL files, okay? In this way, you don't need to compile essentially every time the smart contract if you want, okay? And finally, what you do is you also save the ABI. Now we are going to see what an ABI is. You know, in this way you can, but it's like in Ethereum, the concept is the same. It's an abstraction to communicate with the smart contract engine. And we are going to save it as a JSON file. And so fwrite, fdictify, oh, sorry, JSON dumps. And contract identify. Okay, so now let's see which is the output of our compilation. Okay. Okay, this is our TEAL program, which we have generated from the router essentially and pyTEAL. And then we have all the, this is the ABI, which essentially is, tells us which is the name of the contract, which is the functions that we can use, and for each functions, the arguments and the type of arguments that it takes and the return type of each variable, okay? All of each functions, okay? Okay, great. Okay, so now what we have to do is to, from the TEAL, create a bytecode, okay? Used by the Algorand virtual machine. So we will use another compilation, essentially, which we define maybe here, another function that can be invoked later. Also, compile program. Is it useful for Web 5? What do you mean with Web 5? Web 3? Maybe? With Web ID. No, I don't. I'm sorry, but I actually don't know this thing maybe. So, I mean, if we send me something offline, then we can see it together. But maybe it's something that's a way of calling something that I'm missing, and I don't see the point with sensitive data. Let's discuss this maybe offline, okay? Just okay. Okay, so now we are compiling our program, and to do that, we use within the okay, we need to use also the client and the program, yeah. And from the client, we use compile, and we pass it the program. Okay. Then we will return the base64 encoded of this code. Okay. Sorry, we will decode the base64. Result. So here to this we pass code program. We will have the same for our clear program. Okay, here we are missing one argument, which is our algo client, okay, which is the one connected to the. Okay, and okay, now we have everything to deploy our smart contract. Okay, since okay. Okay, let's print something here. Deploying. The way to deploy smart contracts is as follows. So we need to the creation of the smart contract generates this no open complete action, okay, on complete action, yeah. And so we need to specify that our transaction on complete will be a no operation OC, okay. Then every time you want to send a transaction to Algorand, you always have to retrieve from your client the suggested parameters, and then which are all those parameters that like which is the minimum fee, which is the maybe the round of consensus, and some other stuff which are necessary to validate transactions, essentially. Is there a typing line? 69. Yeah, sorry. Okay, thank you. And so we can create our transaction object, okay, and within this transaction module, okay, we can create all the transactions that we need for Algorand, and you may see that there are a lot for specifying each operations that you want to perform on Algorand. So there is the payment transaction, the key register transactions, and many others, application call, clear state, the ones for creating the asset, destroying the asset, transferring the asset, and so on. So from this transaction dot, you can access all these type of transactions. the one that we need to use is the application create transaction, okay, which we need to specify. So which is our address, okay? Here, account address from private key. Okay, so we compute from the private key our address, which is the first parameter of our application create transaction. Then we pass the parameters, okay, the suggested parameters, okay. Then we pass which is the operation that we want to do on complete. In this case, this is no OPC, but essentially is the creation, because we are not specifying any app ID in this no OPC, no operation, sorry, application call. When you specify the app ID, in this case, it will be 0, okay? But when you specify it, you're doing an application call, okay? And then we specify which is the approval program. Sorry, compiled. Yeah. And then which is the clear program compiled, which is the global schema, which is the local schema. And in this case, we don't have arguments. So as you see, app args, there is no need to specify them because we don't have any application arguments. So we have created our transaction. We need to sign it with our private key. Then we extract the transaction ID from the signed transaction. Get TXID. Then we send this transaction. Oh, sorry, our client. This sign transaction. Okay, then we do some print. So we are creating the transaction, we are sending it with our private key, we're extracting the transaction index, and we are sending it to the network. Okay. Yeah, let's do one try catch here to be more sure. Okay, here now we wait for the response. Okay, and the way to do that, it's very easy. Wait that our transaction is actually added to a block, and from our transaction model, we have this wait for confirmation function, in which we pass the client and the transaction ID. That's why we extracted it, and how long we want to wait for our transaction to be added to the blockchain. Okay, then we can do some print. Once it is confirmed, we say transaction added to the block. Format transaction. No, sorry, response. Okay, if there is some error, we'll print the error. Let's do this. Hoping that there is not. Print app. And we will return. Okay. So let's try to deploy it. Maybe I can print also the, it seems that it worked. I can print the transaction ID in order to see it also on the Explorer. The XID. Okay, so we'll execute it again. Also have this here, but essentially this is our application, okay, which has one counter set to 0. Okay, and we have deployed it. Now the last thing we have to do before having maybe a little break is or even I don't know if how they did in the past, is to invoke one of the methods here. In our case, we are going to invoke increment. We are going to increase the value of our counter. Okay. So once again, we have the okay. We have already computed some stuff. So for sending transactions on invoking a method, okay, in a very light way, we use an object which has been developed by Algorand, which is called Atomic Transaction Composer, which makes us also once again very light the interaction with and easy and the interaction with smart contract methods. Okay, and it should be okay. I need to import it before. Okay. We need to create this object, okay, Atomic Transaction Composer, okay, and we need also to create a signer, okay, which is another way of signing transaction. Sorry, it's an account transaction signer, which is the way that you essentially sign transaction within the Atomic Transaction Composer. And we need to pass to this guy here our private key. Okay. Now it's very easy to call a method in our smart contract. We simply have to add to do this thing, and of course I have to save somewhere our application ID. Otherwise, it won't be. Easy to invoke the smart contract. So once we have our smart contract, we deploy it. We have to, as you see here, every smart contract is identified with an application ID. We need to retrieve it. Okay. So we're going to do that in this way. House code. We are going to access the info of this pending transaction. And then we are going to extract our app ID and transaction response application index. And then maybe we can also print it out. Created app with ID. App ID. Okay, great. Now So the first thing we need to pass to the add method call of the ITC is the app ID. Then the method that we want to use, and from the contract variable we have created above, we have this function get method by name. We can invoke our function simply in this way, and then specify who's the sender. So who's the address of our transaction, the parameters, the suggested parameters. Then this signer object that we have just created, this one here, which will sign our transaction. Okay. And nothing else, because we don't need to pass. Actually, after that, we could pass the arguments of our transaction. Okay, but in this case, we don't need any of them. Okay. Yeah. So to execute the transaction, we need to do this, invoke this function, execute on the atomic transaction composer object, specifying which is the client and the amount of brown that we want to wait. Then when the transaction is completed, we print out our transaction ID. Result invocation tactics IDs of 0. Okay. And okay. So in this way, we, as you see, it's with atomic transaction composer, it's very easy to invoke transaction on the smart contract. Okay. We did it now for increment, but you can do it simply on decrement, simply changing this name here, and in our case it works. So let's run it, hoping that everything works. So we are deploying the smart contract. You see, we have created the app. And this is the second function that modify the state of our variable, okay? And we modify the state of the smart contract. Okay, so I think we did everything for this first example. Let me check, but I think so. I don't know, in the meantime, if there are questions. Yes, something that we can do. It's also reading the global state from our program, essentially. Okay, maybe since time has passed, maybe we can. I can show you that in action, essentially, and therefore from the util here, I'll copy the. We'll see together, but I won't write it. We will use these two functions to read the global state. Okay, so we can do this now. Global state read global state, to which we have to pass the Argos client and the app ID that we have just computed. And what the read global state does in both cases is the following. It access through the client to the info of the application. You can do this for the applications and for accounts. It's very easy to access the state of of either the applications of or the account, you just type client and okay, in this case would be account info, okay, with the app ID, in that case with the address, and then it will return you an object. And in this field here, params global state, there is our global state that we have to format properly to read it properly, because everything, if that is not integer, so an unsigned integer is encoded in base 64. So what we have to do is decoding it in a way to read it. And in this function, this is what we are doing. Essentially, we are decoding the key at first, and then according to the type of our value, we are decoding its value, and both in terms of if it is a bus, we are decoding its value, and if it is an unsigned integer, we leave it as it is, and we are filling this object and returning it back. So let's see it in action, and let's skip to something else. Okay, so we had it. Okay, so maybe we can, I don't know if there are questions. Okay, in like this first example, I wanted to go slower in order to go through the details of the creation of the smart contract and the invocation of the smart contract, and give you more, like in a slower way, all the elements to create smart contracts, interact with them on pyTEAL. I want to skip to the other part of the lecture, where we are going to see one user application, and how to do that on pyTEAL, with pyTEAL, and how to improve actually it and improve its functionalities. Okay. Okay. I don't know that, but the way to interact with smart signatures, it's very, very easy. It's very not easy, sorry, but very, very similar to the one compared here to the one of applications. Okay, essentially, smart signatures are in smart signatures you have to define a logic that approve or not a transaction, and in that case, the state of the ledger that you're modifying is not on an application, but it's on something native, like which is natively created or managed in the blockchain. So, for example, you want to transfer a token only, or a set of tokens on if and only if certain condition holds, from one user to another user, from one account to another account, and so, but the way to define the code is this, like the code of this logic is the one of pyTEAL that we've seen before. What changes is like the way of sending this transaction to the blockchain. But in the documentation, for sure, you will have everything. Otherwise, you can reach me, or also the lecturer of the Smart Signature seminar. Okay, so there is another questions. To gas in a solidity constant context. You know that I don't know the guards in solidity context, so I cannot answer your question, but you can also write me offline and pure functions. Okay. No, because pure functions are those functions in solidity. Yeah, okay. Okay, pure functions are those functions that do not modify the state of the ledger. So you simply, I don't know, you are computing an addition, but you're not saving the result of the addition on the the smart contract, as far as I remember. While modifiers like are smart signatures are like smart signatures are modifying in the end the state of the ledger, so they are not like proof functions. They can be seen as modifiers. I think that they are more closer to modifiers than proof functions, essentially. And yeah, because like you modify the state of the ledger, even only if some conditions in the modifier holds. So like if the logic of the smart signature holds, I would say that they are closer to modifiers in my perspective than proof functions. So let's have like 5-minute break. We breathe a little. I don't know if the other lecturer did it, but maybe you.
Yes, so of course we did. Maybe also
Okay.
more than 5 minutes if you want.
Because I don't have a lot of. I would like to show them some stuff. So at most 10 minutes.
Okay, let's say that we can start at 45.
Okay.
So in less than.
So then
10
I have
minutes.
1 hour to go. Okay.
Yeah, I think that it's okay.
Yeah.
Thank you. So see you in 9 minutes.
Okay.
Okay.
Okay, now you should see the screen again.
Yes.
Okay. So we just go through the details now of creating smart contracts and how to interact with it in pyTEAL and the Python SDK. Now we go through 2 more complex applications, okay, of the smart contract, of creation of the smart contract. We're going to discuss the code together. I won't code it in front of you because they are longer, but I think that there are several inputs that then you can retrieve while while in the future you will work on your projects that will be useful for you. And essentially, the context we are exploring now is the context of auction. I think you have heard about it also in some of the past lectures. So we are trying, in this case, to sell an NFT, and we want to create an auction out of it, and you want to make bidder participating to it and registering and making the smart contract controlling managing the auction. And essentially what we are going to do in this example, in the first example, is that we are going to save in the smart contract state only the highest bid and the bidder that made it. And as soon as the auction terminates, the seller or the creator of the auction, in this case I have that the seller is not the creator of the auction, and transfer the NFT, delete the application while transferring the NFT and the token of the bid of the winning bid amount to the seller, and the NFT transfer the NFT to the winner. Okay, and everything is public in the repo, and everything is available in. This is like the root, and there is the source within the auction file. Okay, there is all the material that we need, the auction contract and the main that essentially calls all the smart contract. This is the code of our smart contract. Okay, and as we did before, we start exploring. Like I suggest you to start writing a smart contract starting from the router. Okay. And here I have my router. Okay, within a function. In this case, I made it. the router is an auction contract that I only define one bear call applications, which is the delete application. That because for the other, all the other bear call actions, we are gonna do like the false behavior, okay, which is the one of ignoring, okay, except for the case of the creation that we will see how I handled it this time, okay. So I will have a different constructor this time. I remind you, bear calls do not want any arguments, okay, any parameters as input. In our case, now we want it. So in this case, our router essentially in the bear call actions only have this handler on delete, okay, which does this set of operations. We'll see later what they do. And for the creation, okay, then we attach to our router somehow all the other methods, okay. Essentially, we are using 1, 2, 3 methods plus the on delete, which actually now I made it I use it in this way, but to show you that you can work in 2 different ways essentially. But from my perspective, maybe I'm missing something, but using this approach with router method and the method down, or this approach is exactly the same if you're not having any input parameter, okay? But since now we are having always an input parameter except for bit, okay? But this is like a simple method, so it does not have, I mean, it doesn't make sense in this case. But you could also have created one def create up and like one def on delete function with a router decorator that within the parentheses actually has additional information that we didn't use before. Okay, in this case we specify that for the no op complete action. So, and in particular when this is a creation, okay, and is not a simple code, okay. So at creation time, we call this create up, okay, function that takes as input all these parameters and returns one output, okay. We didn't see before how to create an output from a method in the smart contract. In Algorand, we'll see it now. And essentially, we are defining the type of each variable. It's mandatory to do that, even though it's Python. pyTEAL won't complete if you do not specify the type of each variable, okay? And the type of variables must be of the class ABI and something else, because in this way, what we are doing now is as we did before I showed you, that we generate an ABI file essentially. So a JSON file with all the signatures and of each function, which the type of each parameters that can be that is used for sorry, please. And these are like, we need to specify these ABI and the type of each variable, because then this information is put in the JSON file of the ABI, okay, that is used for it to interact with the smart contract again. So we can access the type of the ABI from these let me see. Yeah, I need to go here. If you go to the pyTEAL documentation, okay, here you have all the type that ABI support, okay. You can create your own types actually, but there are also some like basic types. These are the basic types, and you see that I'm using some of them. For example, I'm using ABI account, which actually is not in this list. I expect that to be in this list. It's a reference type, so it's a different type. There are basic types and reference types. Okay. This is another like somehow basic type, but it has a different meaning. Like, then I'm using a sign 64 integer, and for all the other input variables. And then if you want to specify the output variables, you need to add this, like this tiny star, I don't know in English, but with a comma, this tiny star, comma, and then the returning value. Okay, in this case, our output would be a string, and in this way you specify which is the output. Okay, and then you start doing a set of operations which are essentially all we are for our auction saving a set of information which are the following. Now maybe I go more into the details of how this auction that I've programmed works, and I'm saving all of them, and then I'm doing some verification. Okay, how this auction works in detail. I have one creator, okay, which creates the application handling the smart contract, and then there is the seller, okay, who's the guy who wants to sell its NFT. Actually, this creator and this seller can be the same person. In my case, I did it two different persons, but they can be absolutely the same person. So the seller could sell the NFT by itself. So the seller creates its NFT, the creator creates the application, and then specifying for the application which is the NFT that will be sold, and which, when the auction starts, when it ends, which is reserved is the minimum amount of money that the seller wants to gain from this sale, and the min bid increment is the minimum amount of increase between one bid and another. Okay, you cannot bid like one micro algo more than another one, but a certain amount that the seller is specifying. Okay, and so I'm setting all this information. Okay, so who's the seller, and which is the NFT, which, when the auction starts, when the auction ends, and all the other informations. I'm saving also who is the guy, this lead bid account key. This lead bid is the bidder who's leading, who's winning. Okay, and I initialize it at 0, like as nothing, and then I'm verifying that the timestamp of the latest block including this transaction is lower than the starting time of the auction, and that the starting time is lower than the ending time. This is because then we need to, before starting the auction, we want to set up properly we need to do some other operation. Okay, and we'll do it in another function, and then we are returning and then we are setting our output, so our returning value, to the value of the address. I just added like as an additional information to show you how to return a value out of a function. Okay, which may be something that, okay, it might be useful as a programming pattern, okay, to use for you in the future. Then the second operation that need to be done is after the creation, okay, it's the setup of the auction, which essentially create. This is interesting because this is the first time we see how to create an inner transactions from a smart contract, okay? Usually, as also in Ethereum, like every chain of transaction, let's call it this way, is initialized by an account, okay? So by a user, but a smart contract can make its own transactions, invoking other smart contracts, the application of other smart contracts, or interacting with the rest of the ledger. Okay, in this case, what we are doing here is creating this type of transaction, which is an asset transfer transaction for our NFT. Okay, and yes, okay, when you transfer. When you want to trade an asset in Algorand, before starting trading it, you need to opt in, doing this operation of opting in, essentially sending a loop transaction from an account to itself, with that which is of type asset transfer, that transfers 0 token, okay? And in this case, we are transferring 0 token, we are not transferring any token, but we are doing a transaction from our smart contract to ourselves, again, of 0 asset for the asset key we want to trade. And this is made for giving authorizing someone to transfer you an asset, okay? Because after doing this operation, we will receive from the seller, the smart contract will receive from the seller the token, okay? In another transaction, we're gonna see it later. And then after the phase, this setup phase, the auction starts, and okay, a bid is made of 2 transactions. Okay, we're gonna see it later also, and because as I told you, you can pack transactions together, group transactions together in Algorand that either commit all together or are refused altogether, even though one transaction is not valid. Okay, they are atomic in some sense. And in this case, we want to retrieve that, we want to this here, yeah. We want to retrieve the index of the transaction, because now we are doing 2 transactions for every bid. The first transaction is a payment transaction, which is a transaction that, as we verify here, who's transferring the bid to the smart contract, okay? So here we see that the receiver of the first transaction, okay? The receiver of the first transaction, the group index is 2, because the transaction invoking instead the smart contract is the second transaction, so this index will be 1, or actually 0, and but will be the first of the 2 transactions. And we will verify that the receiver of the first transaction is the smart contract itself, and that amount is high enough, okay, for being accepted, and that the sender is the same guy, okay? And then we are verifying also that the smart contract owns the NFT, so the NFT has been transferred, so the auction has been correctly set up. The auction has started, okay, and is not over already. And if the amount of the first transaction is greater than the one which is stored in the smart contract plus the minimum increment that the seller wants for each or the creator of the smart contract wants for each bid is enough, then we are going to essentially update our which is the highest bid and which is the sender, so who is the guy who's winning, okay? And then we are going to approve the transactions. But what we did do before is paying back the previous leading guy, okay? We do that with a subroutine, which is another concept available here in pyTEAL. Essentially, we have methods that can be invoked by as a function call, as application calls, application calls. So, and while subroutines are snippet of codes that are we are creating subroutines, so functions that are used by the smart contract, like internal transactions in Ethereum. Okay. So in this case, we are repaying the previous bidder again, and the way to do that is essentially we are creating an inner transaction, okay, as we did before, like with this builder. We set these fields, okay. We specify that is a payment transaction, that we are paying the amount of the bid that he has paid before minus the minimum transaction fee plus. And we are specifying who's the guy who's in it, and then we are submitting this transaction that we are sending it. And this is our bid. And as soon as our transaction auction finish, we allow to invoke the onDelete function so that we'll complete the auction and delete the smart contract from the state of the creator of the smart contract. Okay. We will do a set of controls essentially. So at first we verify that you can still delete the auction if the auction has not started. If the auction has started, and this is the way to do that, and we are also we have also two subroutines that we'll see later maybe what they do, because this part is more interesting, the second part. And essentially, so if someone has bid, essentially, so the leading guy is different from 0, which we have set up at the beginning, we okay, if it is different, okay, yeah, and we verify that the bid amount is more than how much money wants the seller earn, so the reserve amount, we are transferring the NFT to the winner, okay, through this subroutine, which essentially what it does is to create an inner transaction again that transfer the token to the account that we have passed as input, okay? And then the second options, the second thing that it does is, okay, if this, and the second thing that it does is like sending the remaining funding to the seller, okay? This is through these other subroutines, which is closed account 2. And again, it creates an inner transactions transferring the money to the account that we have specified as input, okay? So in this case, we are verifying that with balance, you are verifying that the current applications has some money, okay? Otherwise, this transaction will fail, and our our execution will fail. Okay. And okay, if this condition, so if nobody has bid, like it will return everything back to the proper people. Okay, and then it approves or rejects the transaction of deletion. Then afterwards, our smart contract will be deleted. Okay, and so now we have seen how the smart contract has been programmed, and we now see how to interact with them. Okay, and the way to do that is as before. Okay, we use a mnemonic, and we retrieve the private key and the address of the creator. As I told you, there is a creator and a seller. After that, we create our client. We generate an account for the seller and an account for the bidder. Okay, and then what we are doing here is I'm creating two transactions that I'm sending to the ledger for paying for giving funds to the bidder and the seller. Okay, and then I create the NFT. Okay, and to create the NFT, I've used this util function essentially. Which is defined in the util. Okay, and what it does is creating one asset create transaction. Easy, it prints by itself, and of one NFT of in this case, in our case, our NFT will be one. I made this draw yesterday. This is the Algorand throne of our that is sale on the NFT, and so we are going to sell this Algorand Game of Thrones token, and we're going to sign it, and we're going to create this token, like, and we are sending the transaction as usual, like signing it with the secret key of the seller in this case, and sending this transaction. We will wait, and we will retrieve from response the asset index, because every application in Algorand is identified with an index. Also, an asset is identified with an, or also every asset is identified with an index, and then we are setting like all the others parameters for our auction. Okay, and our auction is created within this function here. Okay, which is always in the same file that takes as input the client, the secret key of the sender of this transaction, which will be our creator, which is the seller, who's the seller, which is the NFT ID when it starts, and all the parameters that actually we need to pass to the constructor of our smart contract somehow. And again, as we did before, we are defining a schema of variables. Okay, local bytes, local ints, local bytes, global ints, global bytes, and as we did before, we are compiling our router. Okay, I also add some optimize option, and then as we did before, we are printing out all the we are saving somewhere the programs, and we are compiling it again with the same functions we have used before, compile program. And then in this case, differently from before, we are not creating the function, we are not creating the smart contract with a simple transaction essentially, but in this case we are using the atomic transaction composer because in this case we are not doing a bare action code, but we are doing an invocation to a method, which is the method that is executed when the incomplete action is no op without app ID. That means that we are creating the smart contract. Okay, indeed, we are specifying all the information for doing that. Okay, and okay, we create our atomic transaction composer, we create our signer, we are obtaining our suggested parameters, and then this is the, you can like then afterwards, like when, if you want to go through the code again, see the difference with the approach that we used before. We are specifying that the app ID is 0, okay? We want to invoke this create app. And we know that, like we have programmed our contract to execute the create app only when only at creation time. So in this way, we are specifying that is creation times, because like by default, the action complete, how's it called? On complete, yeah. Let's see. Yeah, you see, by default, the on-complete action is no OPC, which is the one we need here for creating, no op, but is not, since we are using app ID 0, in this way we are invoking the creation and not a simple code, okay? Then we execute this function, we wait for its confirmation, and we are extracting the application index, okay? And we will read the global state, okay? So now we have created our auction. We are now want now to place, to set up the auction properly. And the way to do that is we need to make the smart contract enable to receive the NFT and transfer the NFT to the smart contract. Yeah, and we also need to give it some funds, essentially. And what we are doing now is, in our setup phase, is creating 3 transactions that are send and commit together to the blockchain. And the first transaction is a payment transactions. We are creating all of them with the atomic transaction composer. Okay, we are creating the transactions like we did before for VCB, how to create the transaction object, the different transaction objects. So we are creating a payment transaction. Then we are differently from, we attach this different type of transaction with respect to the application call in a different way to the atomic transaction composer, okay? And we are doing that, passing it the transaction we have created and the signer object that we have created, okay, as that we have always used. And we attach this object, then we have this transaction then to the ATC. Then we invoke, as we always done, the smart contract with these functions. With this function, we are specifying, like, as you the only exception that it's different now that it's the first time we see it is that to the add method call, we are also specifying which is the asset that we are trading, okay? Or not we are trading, the asset that it's somehow interested by this method execution, okay? Because as you remember, I don't know if you remember, but on setup, you create an inner transaction from the smart contract to enable itself to receive the NFT, which is then transferred to it in the third transaction of this group of transactions, okay? And then we execute this transaction and we print the result of the transaction IDs that we can, in order to retrieve it on the public ledger. Of course, what we need to do afterwards is placing the bid, okay? So we will now our bidder comes into the scene, and it will place its build, and it's easy to understand how it does, given all the things that we have seen. Essentially, it will transfer, as I was saying before, like we have a group of 2 transactions here. The first transaction is transferring the bid amount, and the second transaction is the transaction which is placing the bid somehow on the smart contract. So it's invoking the smart contract, okay? And we group these 2 transactions into the atomic transaction composer that it's then executed and sent to the ledger, and we will read the global state when it confirms. Here there are 2 cases. In the case we reading from the ledger, from the smart contract, we notice that there is someone else that has already bid. We are going to refund it. We are going to refund him in the code, and therefore we need to specify which are the other accounts, except from the bidder account, which are interested in this method, which are accessed by the smart contract. And this is because, as I was saying previously, maybe now it's more clear, on Algorand, you always, with respect to Ethereum, you always have to specify which are the information on the ledger which are accessed. While on Ethereum, everything is somehow made within the smart contract itself, okay? All the information that he can access, you can do that from Solidity directly. While here you have to specify that you have to somehow give some pointers to the validators of the network to access the information which are outside of the smart contract. And yeah, so the last operation is the closure of the auction. And for closing the auction, we are creating a delete application transaction, specifying that which are the accounts that are interested from these applications. So the ones that are somehow accessed by the smart contract, and which is the NFT, so the token which is interested by this, because as you remember, these transactions create I think 3 inner transactions: one paying the seller, one transferring the asset. So no, two transactions, okay? Then we wait for this transaction to confirm, and then we will print the transaction ID. And this is our auction, essentially. Now let's see it in practice, and let's, yeah. So I have to specify here this, yes. Okay, let's hope that it works for the, okay, let's switch back to the, I don't have time to fix it now. So let's use the sandbox. In the meantime, I've achieved to make it work. So we are essentially in the background nowadays, we are founding each account involved. So it's something preliminary for our auction. Auction contract is called, okay. I don't know if there are questions in the meantime. Like, I wanted to go more to see, let you see, give you material to then offline, like check more stuff. Again, this. Like, if you have questions in the meantime, you can type it. Okay, there are two. Okay, so now we should have everything fixed. In the meantime, I've received a question specifying some info outside the contract differently from solidity is a measure of increased security, or it is done since there is a different consensus algorithm. I would say it's not like, because like on Algorand we have to ensure the purpose is to ensure scalability and high transaction throughput. Okay, so if you make the validation of the logic faster, you will have the system would scale. Like, this is my thought about that. Like, it's not for security reason, but it's for performances. Okay. Okay, so our auction went well. Our token was sold in the end. So we, at the beginning, we see that is there a way to, yeah. At the beginning, we are deploying the auction, and this is our global state that we have set. Then we have set up the auction, and after the bid, you see that the bid account has changed, and the bid amount was not in the state, so it was 0. Now it has been increased. One bid has been done, and yeah, and then afterwards there is we are closing the auction, and I'm not printing it out, but essentially we are transferring the token. Okay, so let's go fast to the other example that I want to show you, only because I want to yeah, make it clear that to highlight how to optimize solutions in terms of functionalities, because with this new auction we are gaining more functionalities, but in terms of privacy and yeah, of our bidders, and also increasing the security somehow, because in this second auction we are like it's a sealed bid, so sealed auction, so each bidder is placing a commitment for its bid and a deposit for like ensuring good behavior as an incentive to behave correctly. Then in the second phase it will open its commitment and it will take its deposit back. So when that commitment phase is over, everyone has to reveal, but it cannot change so it's like yeah, a sealed bid, like you put your bid within a sealed letter and you put it in a big box, and at the end you open all the box and you elect the one who's winning without knowing which is the highest bid before the reveal phase. Okay, and so this was one example that was realized in a work that we have done last year with Professor Vitaletti and Professor Visconti as well. And in that case, we have realized these two auctions again. And in that case, we were saving each bid as a global state, okay, as a global state of the smart contract, okay. In this example that I'm showing to you, that I'm providing to you, I'm saving it not as I'm not saving each commitment as a global state variable, but as a local state variable. These for two reasons. Okay, in this way, I optimize the way we are paying for this global space. Okay, it's not on charge of the auctioneer anymore, the seller anymore, but everyone that wants to take part into the auction has to provide a minimum amount of algo, because like every time you want to I think they already told you, but every time you want to trade an asset or you want to opt into a smart contract, you have to provide a minimum amount of balance. Okay, and in this way is not on charge of the auctioneer only, but it's split between all the participants and the auctioneer, so the seller. And so this is a way of optimizing it in terms of like token fee management, let's see. Okay, which also something that can be like an approach maybe for your project, for some solutions that are outside, and you can improve them in this way. And yeah, essentially, to go simply, okay, the code, most of it's like the example before. And the only thing that it's different is that we have, before the bid phase, we have another phase, which is the commit phase. So in between, there are two intervals, the commit phase and the reveal phase. Okay, so we will have that start time is lower than the commit phase, and the commit phase ends before the reveal phase. Okay, therefore we have an additional method which is on commit, essentially, to which we are passing the commitment of our bid to this function, and we are verifying that as we are sending the proper deposit. Okay, we are packing two transactions as we did for the bid. The first transaction is carrying the deposit, the second one is carrying the commitment. So for each commitment that we receive, after the proper evaluation, we are saving in the local storage of the of the bidder. Okay, so we retrieve its storage space from the sender of the transaction. We are saving its commitment in its local, like its local as a local variable. Okay, because afterwards on the on bid phase, we will verify that. Once again, here we have two transactions that we are sending, and one invoking the application, essentially the logic, and the second one, the first one again is a payment transaction, which is actually transferring our bid. Okay, and we are doing in this phase, we are using until we are able to compute some cryptographic functions, like we can verify signature, we can compute hash, different type of hashes. Actually, there is also now, like in the most recent update, also the possibility to compute a verifiable random function in a smart contract, which is something very interesting if you want to add some random functionality to your applications. So I mean, it has been added like very recently. There are some opcode that I assume also on pyTEAL there is the way to use them. Like to use this verifiable random function, you can go through the blog, I think Algorand blogs, and see how to use it. Okay, but it seems something promising for good applications as well. But okay, let's go back to our application, and in this case we are verifying that the transaction carrying our bid, okay, it's hash. Okay, here we are converting it from integer to byte. Okay, etop stands for int to byte, of course, and there is also a toy, so byte to integer function. And if this is the same of the commitment that we have sent before, that we are retrieving through this, we are updating, like we are changing local variable. Essentially, we are using one for saving the value, and we are actually, maybe we can also not use it. We are deleting our local variable, and we are saving the value which opened this commitment as a local variable, and then we are updating as we did before, which is the highest value. Okay, and for the rest it works as we did before. And of course, the only thing that it's different is when we are repaying the deposit to the guy who has opened correctly its commitment. So through another subroutine which does in a transaction paying the guy. Okay. Here it's like in this committing option, like in this part, it's like before, there is only one function more. I'm going faster because I want to at least comment a bit bigger with you, even though I think that you have seen that before with Chris, but at least like from after having seen how pyTEAL works, how to see like how to connect it bigger, somehow all the knowledge that we have gained today. And essentially the only function that we can discuss somehow is this one, the commit. This function here, which does the commitment. And what I can suggest you to pay attention to is encoding, okay? And the commitment, I had to go through some work to understand that the commitment needed to be encoded in this way, okay? So pay attention to the way sometimes things does not work out because the encoding is not correct, and this was the way I found out from a value which I pass as integer to this function, turn into bytes of an array of 8-byte ordered in a big endian way, and I compute the hash of it, and then like from this hash I turn it back to like an array of bytes and bytes object in Python that I pass to the smart contract. Okay, and in this way I could make this part of the evaluation of the hash, which was the most trickiest part, working out. Okay, using the amount of the transaction. Okay, so accessing the information from the transaction itself. Okay, I don't know if there are questions so far. No. Okay, so last thing we are going to see in the last 10 minutes. You can lend me 3 minutes if you want, if you can. And okay, Bigger, it's a way to make much more easy the way to interact with the smart contract with respect to all the work we have seen before. However, the only thing maybe I can say about it, it's still in development. So some things it's from my perspective, it's in, I don't know, maybe okay, it's somehow the documentation it's not so complete still, but like the way to interact with the smart contract and create a smart contract, it's very light actually. And instead of having a router, okay, for managing your smart contracts, this is actually our smart contract in Beaker, okay, and this is all the code for interacting with the smart contract. Okay, in this case again, we will have a counter application. Okay, this is the function. Okay, for every smart contract, we define it in Beaker as a class that inherit this application class from the Beaker module. Okay, we define the variable, the global variable in this way. Okay, it's very easy to do. We only need to specify which is the type, and then from this application state value, we specify which type of it's this variable, and we can also attach a little description. Then this is the way to initialize your smart contract. Okay, we create using this decorator create above it, and like in the end invoking this function that initializes as the documentation suggests. No, doesn't suggest it anymore. Yeah, that initialize all the state variables that are declared. Okay. Finally, this is the way to define method. Okay, that can be invoked by users, and there is also a way to define an access control through this class authorized, and I guess you can specify or like who only a specific address, who holds a specific token, who has opt-in for this application, not anymore. Then you define the function. As before, you need to pass the output in using this star and then output. Okay? And then, like we did in before for pyTEAL, you have to define a sequence of operations. And I think that if you want to access when you access a variable in the state, you have to use self counter because it's a state variable of the class. Okay, but somehow it's a mix of pyTEAL and the way to access global variables. It's much lighter, of course, and yeah, but okay, this is somehow pyTEAL. Okay, and as we did before here, in this way we decrease the value. Okay. Also, the way to interact with the smart contract, it's very light somehow, and we don't have to go through all the compile of the approval program and the clear state program and so on and so forth. We just need to invoke this function application client, passing it the client, the class, that we want to, the smart contract, so the class of the smart contract somehow, and assigner again, okay? Then we create our application, and this create will invoke this function, okay? Of course, and we will create deploying the smart contract, and then we will for invoking the smart contract we use this app client call, and we pass as input the method that we want to increment. And I mean, it's very fast way to with respect to the one we have seen before. Behind the hoods is happening all the stuff we have seen. In this way, we are abstracting it in a very light way. So yeah, I don't know if there are questions about it. You can see it working in the meantime. Oh, that's good questions, actually. Let's see. Let's see. Beaker documentation is. Yeah, here. Logic signatures, yeah. Here it is. Yeah, there is a way to use logic signatures also in Beaker. Logic signatures, it's the same of smart signatures. Other questions? Okay. So I complete my tutorial for today. I mean, the repo it's already public, so all the material that I've used today it's already available to you. I'm just updating it, I'm doing a commitment in a while for if there is something wrong to fix it. Still, if there are no questions, thank you for the attention.
Okay, thank you very much for the presentation.